Hello everyone and welcome. Today, we are going to discover the secret unlock code for matrices. Seriously, this is a super powerful tool that lets you solve some really complex problems in just a few simple steps. So are you ready? Let's dive right in.
Okay, so take a look at this system of linear equations. Now, I'm sure you've solved these before using substitution or elimination methods, right? But what if I told you there's a way to solve the entire system with a single, powerful undo button for the matrix? I mean, this is the kind of math that powers everything from your favorite video games to complex engineering. Sounds cool, doesn't it? Let's find out exactly how it works.
So that special undo button is called the inverse of a matrix, and we write it as a to the power of -1. Just think of it like pressing Ctrl-Z on your keyboard. It literally reverses the operation of matrix multiplication, which is incredibly useful for solving equations.
Our main mission, really, is to solve equations that look like this: ax equals b. Here, A is the matrix with all the coefficients, x is the matrix with the variables we need to find, like x and y, and b is the matrix with the constants on the other side. So the puzzle is, how do we get x all by itself? Well, we need to somehow cancel out A. And for that, we need its inverse, A inverse.
Here is the golden rule you have to remember. Whenever you multiply any matrix A by its inverse, A inverse, you get the identity matrix, I. You can think of the identity matrix as the number 1 in the world of matrices. Multiplying by it doesn't change anything. It just brings you back to where you started. This property is the key to everything we're going to do, so lock it in.
So the big question is, how do we actually build this inverse, this unlock code? Well, the very first ingredient in our recipe is something called the adjoint of a matrix. Let's see how to craft it. Now, I know the definition sounds a little technical, but trust me, it's really just a two-step process. First, we find something called a cofactor for every single element in our matrix. Once we have all those cofactors, we arrange them into a brand new matrix. And for the second step, we just take its transpose, which just means we flip the rows and columns. And that's it. That gives us our adjoint.
And you know what? For 2x2 matrices, there's a fantastic shortcut that will save you so much time in your exams. It's a real quick win. Just look at the matrix. First, you swap the elements on the main diagonal, A and D. Then, you just change the signs of the other two elements, B and C. That's it. In 2 quick moves, you've found the adjoint. Super easy, right?
Okay, that 2x2 shortcut was a nice warm-up. But for a 3x3 matrix, we do need the proper general method. It involves finding things called minors and then cofactors. Yeah, it takes a few more steps, but I promise you, it's very systematic and completely manageable. We'll break it down together. You're doing great so far.
Right. Here's our 3-step plan. First, we have to calculate the cofactor for each of the 9 elements. Now, to get the cofactor, we first find the minor. You just pick an element, cover up its row and column, and find the determinant of the 2x2 matrix that's left. Then, we give that minor a sign, either plus or minus, based on its position. The signs follow a simple checkerboard pattern. Easy. Second, once you have all 9 cofactors, you arrange them into a cofactor matrix. And for the final, absolutely crucial step, you find the transpose of this cofactor matrix. That final matrix is your adjoint.
Now listen up, this is a pro-gamer move to avoid a very, very common mistake. So many students calculate the cofactor matrix and then just stop there. But please remember, the adjoint is the transpose of the cofactor matrix. You absolutely must do that final flip of rows and columns. Don't fall into this trap.
So, we have our first ingredient, the adjoint. Great. Now for the second part of our recipe, we need to meet the gatekeeper. And this gatekeeper is the determinant. It's the one that decides whether we can even create an inverse in the first place.
This brings up a really important question. Can every single matrix actually be inverted? I mean, does every lock have a key? What do you think?
The answer is a clear and simple no. And this is probably the single most important rule to remember from this entire topic. A matrix has an inverse, we say it's invertible, only if its determinant is not equal to 0. If the determinant is 0, sorry, the lock has no key. Game over.
So, the determinant gatekeeper gives one of 2 verdicts. If the determinant of A is 0, we call the matrix singular. This means there's no unique solution, so no undo button exists for it. But if the determinant of A is not 0, the matrix is non-singular and we get the green light. We can go ahead and create our unlock code.
All right, we've got the adjoint, and we've just passed the determinant gatekeeper's check. It's finally time to put these two pieces together and reveal the master formula, the ultimate unlock code for our matrix.
And there it is, the master key. The inverse of A is simply the adjoint of A multiplied by 1 over the determinant of A. You can see so clearly how the two big pieces we just learned about, the adjoint and the determinant, come together perfectly to form the inverse. This is the formula you need to master. And you might be wondering, where does this formula even come from? Well, it comes from a really important property. Any matrix A multiplied by its adjoint is equal to the determinant of A multiplied by the identity matrix. If you just do a little bit of rearrangement on this equation, you get our master formula. See? It's all connected.
Okay, enough of the theory. We've built our unlock code, we have the master formula. Now let's jump into a practical example and see how to use the inverse to solve a real system of equations. Let's put it to work.
The method is beautifully simple, and it's just 3 steps. Step 1, always check with the gatekeeper first. Calculate the determinant and make sure it's not 0. Step 2, use our master formula to calculate the inverse, A inverse. And finally, step 3, the solution is just a simple matrix multiplication. X equals A inverse times B. That's the whole game plan. Let's solve this system. 2x plus 3y equals 1 and 4x plus 5y equals 2. The very first thing we do is write it in the matrix form AX equals B. So our matrix A is the coefficients 2, 3, 4, 5. X is our variables, x, y, and B is the constants 1, 2.
Okay, step 1. Let's check the determinant. For our matrix A, that's 2 times 5 minus 3 times 4, which is 10 minus 12, giving us negative 2. Perfect. Since it's not 0, the gatekeeper says we can proceed. Next, we find the adjoint using our 2x2 shortcut. We swap the diagonal elements to get 5 and 2, and we change the signs of the others to get negative 3 and negative 4.
Now we're ready to find the inverse using our master formula. A inverse is 1 over the determinant, so 1 over negative 2, multiplied by our adjoint matrix. We just multiply this negative 1/2 into each element of the matrix, and we get our final inverse. And now for the final step. We calculate X equals A inverse B. We multiply the inverse matrix we just found by the B matrix. We perform the row by column multiplication, and we find that the matrix X is 1/2, 0. This means our final solution is x equals 1/2 and y equals 0. And just like that, we've solved it.
All right, let's do a super quick recap. Remember, the inverse, A-1, is the ultimate undo button. To build it, you need the adjoint, which is the transpose of the cofactor matrix. Don't forget that transpose step. The determinant is the gatekeeper. If it's 0, no inverse exists. Our master formula brings it all together, and we can use it to solve systems of equations with the simple formula x equals A-1b.
So we have successfully learned how to find the unlock code for non-singular matrices. But that leaves us with one final very interesting question. What happens when the gatekeeper says no? What do we do when the determinants of a matrix is 0? Think about that. We'll explore it in the next one. Thank you for watching.